Recursion today. One in the morning and one in the afternoon. I'll say that the one in the morning is probably kind of more like the problems that you will see, problem you will see on the interview or the coding assessment. The one in the afternoon is a bit more involved, and we'll kind of look at that from more of like an educational perspective. But the one in the morning is probably representative of the depth or the complexity of recursion problems that will ask you to look at. So the simplest definition for recursion that we hear pretty much everywhere is, oh, a recursive function is simply a function that calls itself, right? And that can be kind of like a mind trip if you think about it too much. But let's start with a little bit more understanding of kind of like why use recursion in the first place, right? I mentioned yesterday how recursive functions are really nifty to solve certain problems, but for the most part, we don't really see them that often, right? And the reason why is because most recursion problems, just like most problems in computer programming, you can solve a variety of ways. And recursion tends to have a little bit more of traps or a little bit more things you want to be more careful about. And so a lot of times recursive problems can just be solved with traditional iterative approaches. So whether it be like a for loop or a while loop or something that's maybe a little bit more easy to understand. So just know that when we look at the problems today, we'll ask you to solve them using recursion. But by no means is that the only way of solving it. In fact, if you solve these problems kind of organically in the wild, it might make a lot more sense for you to do a for loop or a more iterative approach. However, the main benefits of recursion is recursion. The main thing that I'll say about recursion and kind of how it's different from iteration is recursion is really good at kind of breaking down a fairly complex problem into its most simple, most kind of not purest, but its most foundational state. Recursive functions, for the most part, solve only one problem, but the fact that it calls itself means it can solve that problem, infinite times, or at least solve it multiple times really, really quickly. So when we look at recursion, one of the things that we can't really one of the things we can't really ignore is this idea of a call stack. A call stack is pretty fundamental to all programming languages. So in JavaScript, one of the things you'll notice, especially when we write a page of code, is for the most part JavaScript reads it top down, right? But not only is it reading it top down, one of the things we also kind of taking for granted up to this point is if I write a code on line 1 that says let x equal 6, on line 2 I write console.log x. The idea is we expect it to console log out 6, right? And the reason why it does that is because we expect let x equal 6 to finish running before console.log runs, right? And so this is this can be thought of as almost something called threads. It's another kind of terminology. But the idea is if you have a single thread, right, it can only do one thing in a very particular order. And so JS is single threaded, meaning that every function has to run and a function has to finish before the next line of code or the next command starts, right? So when a computer looks at a page of JavaScript, there's no I hope this one finishes on time before I start the next one. The computer is very sequentially saying, I will run this, wait for this to finish, I will run this next, wait for this to finish, I will run this next, wait for this to finish, and so on, all the way until it finishes all the code on the page. So when we think of a call stack, the idea here is the best analogy that, not me in this case, but kind of the traditional analogy that people use for describing a call stack is think of a stack of plates at the buffet line, right? The idea is if I have a plate and I put it on this little kind of plate holder, right? I put it face down. It is now the only and the first plate on the stack, right? However, if the dishwasher washes 5 more plates and he or she brings them over, then what they'll do is they'll put the plates on top of the other plates, right? What that means is now we will have 6 plates, but the very first plate we added is on the very bottom, right? And in fact, if any patrons were to come and grab a plate to get some food, they would grab the plate at the top of the stack. And so this represents a kind of a very core principle with regards to the call stack in JavaScript, which is basically the last thing that gets added is the first thing that gets done next. And we call it like last in, first out, LIFO. There's a few other ways to think about queues. Or rather, this is an example of a queue, like a line, basically. And so if I think about something like function first and then function second, while I go through it, the call stack is actually pretty simple, right? In this case, I define all these things. So between lines 1 through line 12, nothing runs, right? All I'm doing is creating a bunch of variables, which are commands, don't get me wrong, but like it's like we just create a variable on line 5, we create a variable on line 9, and then we get to line 13, and it's the first time we're executing a function, right? On line 13, what we do is we execute this first function, right? And so when we execute this first function, the first function, think of it as like the first plate we put on our stack, okay? And the single-threaded nature of JavaScript means, hey, we need to finish this first command before we need to finish running this first function before we look at anything else. So when this first function is kind of added to our call stack, we jump back over and say, okay, great, let's get rid of this first. Let's resolve this. We go in here, we console log out I am first, and then now we're done with the first function, right? Once we're done with a particular command, or once we finish resolving it, we take the plate off of the stack, or we finish running the function, and then we move on to the next line of code, right? So now that we've finished running this first function, we then say, great, what's my next command? Well, my next command is running this second function. So now I take this second plate, if you will, I put it on the empty call stack, right? Because we've already resolved first. So as of right now, there's nothing on the call stack anymore. We put the second function on the call stack. We finish running. We then execute the second function. We console log out I am second. We finish running it. We take the second plate off of the call stack. Our call stack is now empty, and we have no more code left to run. So therefore, we finished executing this page or this piece of code. So here's a visual demonstration of how that looks, right? On line 13 there, imagine that this is our call stack, right? Like this is the first plate. If we have another plate, we put on top of this, on top of this, on top of this, etc., right? So the first thing we do is we put this first function there. We then execute it, and then we take it off, right? Then we go to the next line of code, which is a second function. We execute it, I am second, and then we finish it. We take it off, and now we're done with this page of code, right? So conceptually, it should be pretty simple, especially for these kind of single one-off things, which is that in JavaScript, we don't move onto the next line of code until the previous line of code has fully finished running. Okay. So then, if that's the case, then you might be asking, well, great. Like if we run each line of code, you kind of like in order, when will we ever have a stack, right? When just each thing like we put on there, resolve it, we put on there, resolve it. When does a stack happen? Well, a stack happens essentially when we have to run something that's dependent on something else. So here, once again, right? So let's kind of skip lines 1 through 10 for now. We look at line 11. That's the first time we run any code, right? And it's this first function. So this is the first kind of plate in our stack, right? We're trying to run for the first function, which is great. So let's go to the first. What happens here? Oh, well, this is the first thing we do is we console log out I am first. Great, so far so good. And then on line 3, it says, hey, do you mind invoking the second function for me, right? And now here's kind of like where the dilemma comes in, right? Is that like we can't take this first off of this call stack because we haven't finished running the code yet, right? Like we're still in the middle of this function. We haven't finished running it yet. But in order to finish running this first function, we need to do what? So we need to finish running the second function, right? And so here's why we now put this second function on top. Rather, we add it to our call stack. Everyone follow so far? Okay. And because this second function is now here, not only do we need to finish running second, but because this is now at the top of our stack, we're going to prioritize running second. Remember, we cannot move onto the line 4 until we finish line 3, right? JavaScript, that's the point of single threading, is that we have to finish the first line before we move on to the next line. So now we have to finish running this second function before we move on to line 4, which will then enable us to finish running the first function. So when we go to the second function, what happens? We console log out I am second. And now we finish running the second function. And so once we finish running that, we can now take the second off of our plate, or off of our call stack, right? And then when we look at our call stack, we'll say, okay, great, where did we leave off, by the way, before I took this detour to run second? Well, I had to run second on line 3, so by the time I finish running second, I'm moving on from line 3 to line 4, and line 4 just says console log out first is finishing. So I run that, and now I've also finished running the first function as well. And now my call stack is empty. There's no more next line of code after line 11. So now the computer says, okay, great, I'm done running this page or this piece of code. Any questions with this so far? Okay. Don't underestimate drawing out the call stack. In some of the problems for today, drawing out the code stack may be a really, really good way for you to visually understand kind of the order in which JavaScript's calling some of the functions. Okay. So let's write a simple function here, and this one I'm not going to belabor the point. This is a for loop, right? We're counting down from 5 all the way to 1, right? If you notice here, we have our normal for loop, except now we're starting at I equals none, right? We're doing I is greater than or equal to 1, and we're decrementing I with each iteration. So we start at 5, then we go to 4, 3, 2, 1, and then we stop when I reaches 0, right? Because 0 is not greater than or equal to 1. Okay, so that's a normal for loop, and it does the job perfectly fine. However, if we were to run this now, if we were to really think about kind of what this function is really doing, this is also an equally valid way of writing what we just wrote, right? Rather than using a for loop, we can write a function that just logs the number, right? And we call it 5 times in a row. It's obviously a lot more manual, a lot more cumbersome, but this also gets the job done, right? This will give us the same output that we were looking at before. And the reason why we kind of we want to show you this way is because remember how I was telling you earlier that recursion really is just breaking down a problem, or sorry, a recursive function is a function that kind of solves like the most pressing immediate problem, like kind of on the table, so to speak. Well, in this case, logging out a number is the most pressing immediate problem that this function does, right? Like really, like once we know what number to give it, all we want to do is give it a number saying, great, log this out, and you're done. We don't need any loops to do that. In fact, as long as something says, you give me any number and I'll just print it out for you, we can give it out any number we want in whatever order we want, as many times as we want. And so we also notice here now that each number that we give it is just one less than the one before. So what's another way of solving this? Let's think about like how this function would now look, right? We have a countdown function, and look at line 8. This is still the fundamental problem that we were solving earlier, right? We're still logging out the number that that we get, except now we do something else. We say, hey, let's also log out the number -1, or rather, let's invoke the countdown function. So let's actually look how this is going to run in the wild, right? Let's say I call countdown to 5. I pass in 5, and once again, the first thing that we do is we say, well, I just want my function to log out a number, right? So the first thing when I do countdown 5 is it's going to log out countdown 5, or it's going to log out 5. The next thing I want to do is, well, I also want to log out the next number in line, right? Because remember, when we do a countdown, we're just trying to get 5 minus 1, minus 1, minus 1, minus 1, etc. So to count down to 5, all that matters is I want to log out my number, and I want to set off something that will log out the next number. Okay, so count down to 4. And so when I execute line 9, if num equals 5, now line 9 is going to say, okay, great, you need to execute this function that's called countdown to 4. So now I need to add it to my call stack, right? Notice I'm adding it on top of countdown to 5 because I have not finished countdown to 5 yet, right? Countdown to 5 only finishes after I finish running lines 8 and 9. I'm in the middle of line 9, so I can't say I finished running countdown to 5. And in fact, countdown 5 only finishes once countdown 4 finishes, right? So let's look at countdown 4. Well, how does countdown 4 work? Once again, all we care about is we log out my number, which is 4, and I want to be responsible for setting off the number that's 1 less than me, in this case, 3. Right? And so what does countdown 3 do? Well, I want to be responsible for logging out my number, which is 3, and I want to be responsible for logging out the number that's 1 less than me, right? And in fact, if we keep going, we'll notice something that's kind of scary is that we actually never stop, right? Because here we're just saying, let's just do num minus 1. Well, numbers don't care, right? 0 minus 1 is still a number, right? It's still, so let's just keep going infinitely. And in fact, eventually we'll see this error. It's called a maximum call size stack exceeded, which basically means they're trying to run like something that runs on infinitely, or at least the computer thinks it will run infinitely. So it's going to try to kind of help you understand that there was an error somewhere, okay? But fundamentally, does this function make sense to you, right? It's like, if I was just take this countdown problem and really boil it down to its main components, what am I really concerned about? All I care about is I log out myself, and I'm responsible for like kind of tipping over the next domino, right? I don't need to plan out all the other dominoes after that, because all I know, because I know that if I tip off my next domino correctly, that next domino will do the same thing. It will say, I'm going to log out myself, and I'm going to log out. I'm going to trigger the countdown for the number that's one less than me, right? So that will be responsible for knocking out the next domino, and so on and so forth. So each problem is actually super simple, because there's just two steps. I'm responsible for logging out myself, and I'm responsible for tipping off the next event in the sequence. The reason why our function basically went haywire and that it started going on an infinite loop is something that's super critical to understanding recursion or writing recursive functions. In fact, I would say that the most important part of writing any recursive function is defining something called the base case. If a recursive function is a function that calls itself, the base case is basically saying, well, when do you stop? Right? Like calling itself is good in theory, but if you don't know when to stop, then every single time you're going to eat up all your computer's memory doing, approximately like infinite calculations, right? And so every recursive function is going to need a base case. If you're ever looking at your code and you're like, oh, I wrote this recursive function and I don't understand why it's not working, like the first step is, what is your base case, right? When does it stop? And so for us, if we were to go back to our countdown example, when do we stop? Well, we know that if the number is equal to 1, if the number is equal to 1, or in this case, the number is less than 1, we're done, right? We're count down from 5 to 1. If we ever reach anything less than that, then we're finished. And so, if we write something like this now, right? If num is less than 1, we constant log out done. Else, we do literally what we just talked about, right? If the number is greater than 1, if it's like 5 or 10 or 3 in this case, we once again log out ourselves, and we say, hey, next number, log yourself out too, right? Notice how in this case, like this is very different from the way we've written out our function so far. So far, when we run our functions, we've planned the entire thing, right? When we write a for loop, we're planning out not just our run, but all future runs as well, okay? In this case, if you kind of put yourself in the shoes of the function, you're only worried about yourself, and you know that if you know yourself well, like down the line, like other things will also kind of follow the same rules, right? So in this case, every iteration, in every call of the countdown function, the function really thinks, okay, my commands are, if someone gives me a number that's less than 1, I'm just going to say stop and finish. Otherwise, I'm going to say, here's my number, and I'm going to set off this chain for the number of myself minus 1, right? And so if we look at the call stack for this now, when we do countdown 3 is going to go through and say, okay, great, is num less than 1? No, it's not. It's a 3. Great. So now we're jumping to this else statement. We're in line 8. We console log out 3, and then we do countdown of 2. Countdown 2 is 2 less than 1? No, it's not. Great. So we're in the else statement again. We console log out ourselves, and we do countdown of 1. Is 1 less than 1? No, it's not. So once again, we're jumping to line 8. We console log out ourselves, which is 1, and then we do countdown of 1 minus 1, which is 0. And now we say, for countdown 0, is 0 less than 1? Yes, it is. Great. We console log out done. And look at that. We're done, right? We never call anything else in the rest of this line, right? We skip over this else statement because we met the if clause, right? Our base case basically told us, hey, you are going to infinitely call countdown on yourself minus 1 unless you hit this condition. Once you hit this condition, the console.log, you run console.log, and there's no other code to run, right? This if-else block ends on line 10. After line 10, we're done with the function, right? So this means we've now finished with this countdown of 0 function. And once we finish the function, what do? We take it off of our call stack to let the person know, or to let the computer know that, hey, we finished running that now. We're done. Okay, great. Now that we finished running countdown 0, the next thing, or where we left off was, we ran countdown of 0 to finish running countdown of 1, right? And with countdown of 1, we left it off right here, right? Countdown of 1, Well, if we finish running countdown 0, it means countdown 1 says, okay, great. What else do I need to do to finish running countdown 1? And the answer is nothing, right? We went into our else clause, we ran these 2 lines, and now after line 10, there's no other code to run. So now we've also finished running countdown of 1. Well, we were running countdown 1 so we could finish running countdown 2, right? Once we finish running countdown 1 here, what else do we need to run for countdown 2? And the answer is nothing, right? Once again, if else clause, after running countdown of 1, we're on line 10 now. There's no other code to run. So we've also finished countdown 2, and the logic holds for countdown 3 as well. In that we ran countdown 2 so we could finish countdown 3. After running countdown 2, there's nothing else to run for countdown 3, so we're done. And now our call stack is empty. There's no more other code to run on the page, and so we finish running this function. Right? So this is like the kind of quintessential example for a recursive function, right? Is that like we write all these functions that kind of call itself indefinitely, and at each single step, the function is faced with honestly a pretty simple decision, which is, do I stop or do I keep going, right? If I stop, then I obviously don't want to do any more recursive calls in here. If I want to keep going, then I'm going to recursively call myself with an input usually that's going to get me closer and closer to stopping, right? And when I say get me, it means like get future runs of myself closer and closer to stopping. In this case, we're getting ourselves closer and closer to stopping by subtracting 1 from our number. But there could be other ways to do this too. So yeah, does this make sense, John?
It makes sense. But one thing I noticed, I was trying to practice recursion yesterday, and when I made this, I did exactly what you did. Instead of being done, I just did return empty, and then it just stopped. But for line 9, I did num minus minus, and that doesn't work. But if I do minus minus num, it works.
Yeah, num that has more to do with like the minus minus syntax, in that it evaluates after it uses number, then it evaluates it. So it has nothing to do with recursion. It's more like of the num minus minus syntax.
But in like the for loop, I can do I++, and it works. But in recursion, you can't do plus plus.
No, this has nothing to do with for loops and recursion. It's the idea that like when you do it in a for loop, it evaluates n first, then it goes to the next iteration of the loop, which is almost like a new function call. In this case, when you pass it in directly, it's going to pass in the number first, and then it will do minus minus afterwards. So it's like I can answer more about it, but if you want to look up like the minus minus or the plus plus syntax, like really kind of just like read through on that and kind of understand the sequence in which it does things. That's like that question has more to do with like the use of minus minus and plus plus as opposed to the difference between for loops and recursion.
Okay, because I only noticed it during using recursion. That's why I'm like, why isn't plus plus working? Like,
yeah, and for the most part, like recursion is just like any other function call, right? Like recursion is more of an idea or a concept. There's nothing here from a programming standpoint that we haven't done that we could not do with normal functions, that we haven't done with normal functions already. So if you try doing that with like any function, it would not work, not just recursive functions.
Is there like a scenario when we should use something like this instead of a for loop and vice versa? Like,
yeah.
I feel like this is the same thing as a for loop.
Yeah. So like I said, like for this morning, like just use like these simpler problems to practice solving problems that yes you could solve it with iteration, but for now practice it with recursion. And in the afternoon we'll talk about kind of other classes of problems I can only solve with recursion and not with for loops. Any other questions? The call stack makes sense, right? Like today, like if you're hung up on a problem, like I'll make you draw the call stack for me, because like that shows you understand on a step-by-step basis what's actually happening. Like the call stack is super critical.
But I like the call stack a lot. It's much more simple to me than the pancake thing that they used to do. Like,
oh, the pancake thing. I mean, it's like a stack of like spherical flat figures, but yeah, I guess like the point of the call stack and the point of the call stack that's like it's really cool because it really kind of like how like I talked about computers are not good with ambiguity. Like the call stack is like the end all be all of like the direct like binary decision making process of the computer, right? Like a computer doesn't need like oh, I wonder what I should prioritize next. Like, nope, I have a stack of plates. I'm going to go to the next thing. I finish one, I'm going to the next one, right? Like at every single point, it's completely transparent to a user if you look at the computer's like call stack or its memory, like what it's going to do next, right? So it's just like it's like the ultimate kind of like precision of the computer, which I really appreciate, right? Because like if you give a bunch of work to a person, right, they're like, oh, I could work on this first, I could work on this first, I could do half of this and half of this, and whatever, it gets like kind of like really ambiguous. So the call stack, like, no, like these are the things I'm going to do in this order, and I'm not going to move on to the next if I finish this one thing. So countdown, 2 takeaways. 1, always have a base case. If you don't have a base case, your function is most likely going to spiral out of control. It will call itself infinitely times, and your computer will probably kind of throw an error at you. Computers nowadays are very adept at sensing when something is more likely an infinite error, and it will stop it beforehand. In the old days, we didn't have the luxury, so it actually would take down a computer. So I guess we have a little bit more better safeguards now. And then secondly, this one I kind of hinted at, right? Like it's kind of like a for loop or a while loop. Like every iteration of this should get you closer to the endpoint. You never want to have a function that just keeps running and you're like, I don't know when it stops and I don't know how I'm getting there, because then you're setting yourself up for just kind of this infinite failure too. Okay, so in the previous example, the function was just console logging something out, right? Which was like we talked about. It's super harmless, super simple, super straightforward. When we add returns to this process, it gets a lot more hairy very quickly. I know, like specifically speaking, like even just from the workshops, I know like the concept of returns is still something that like is some folks I think are still like having trouble with in terms of kind of intuitively understanding. I'll just say this for now. I'll say this like one last time maybe for this cohort. Like return ends the function, right? Like return ends the function. If you have a return in a for loop, it doesn't matter what the for loop's going to say. It's going to end the entire function. Okay, like don't put return anywhere if you're not willing to end the function at that point, right? Like if you're writing a function, you have a return there, nothing else in your function is going to run at all after you do the return. I cannot stress that enough. Okay, don't say, well, I want this for loop to return this here, and then the next iteration will return something else, and the next iteration will return something like that doesn't work, right? JavaScript, once it sees the return function, it says, great, this function is done. I'm taking it off my call stack. I'm finished. There is no like next step after you return it. Okay. However, if we think about the way the recursion works, each time what we're really doing is we're calling a new function, right? So in a recursive function, it's actually not impossible to return something, or rather, it's not a full pot necessarily to return something, because if we have a recursive function, in the previous example for countdown, if we were returning a number each case, that just means, hey, for countdown 2, return a number. Well, countdown 3 called you, right? So those two are independent functions. So returning when you're calling countdown 2 does not impact countdown 3, other than letting countdown 3 know that countdown 2 is finished. So let's take a look at a few more examples about how returns kind of really play a role here. Okay, so one example that kind of demonstrates really well is where we're trying to kind of go through a series of numbers, and the factorial operation is typically speaking like one that exhibits pretty well, right? So mathematically, factorial is just the product or the multiplicative total of all the numbers from a number all the way down to 1 or 0, depending on how you want to talk about it. So like 3 is just 3 times 2 times 1. 5 is 5 times 4 times 3 times 2 times 1. Right? Everyone see the pattern here? And just this is math, but like you don't even know how factorials work. Just take it for granted. Like right now, when we look at this problem, it's just if I give you a number, it's just every number less than a number multiplied together. Okay. So if you were to write this in a recursive function, right? What's our base case? Well, our base case, what are our two paths here, right? Our path are either I stop or I keep going. Okay. What does keep going mean? Well, keep going basically means I want to keep finding the factorial of the number less than me, right? And if you really think about like kind of like what's like the single problem that this is solving, right? If I was to ask you what the factorial of 6 is, and I was saying, hey, here's a 6, like if I was a number 6 would just say, well, the factorial of 6 is 5 multiplied by the factorial of 4, right? Like, well, right? Like, factorial of 5 basically is 5 multiplied by the factorial of 4, right? At any given state, the factorial number is just that number multiplied by the factorial of the number 1 less than it. Good? Okay, so if that's my micro problem, then really the question now becomes, when do I keep going? Well, I keep going if a number less than me is valid, right? So when I look at the pre-example here, like when does a number not become valid? Well, the only one that really looks to be kind of weird here is like, it looks like 1 factorial is 1 and then 0 factorial is also 1, right? 1 factorial actually kind of makes mathematical sense too, right? It's just 1 multiplied by nothing. I mean, it's just 1 itself, right? But the 0 here is like, well, 0 multiplied by 0 is should give me 0, but it's giving me 1, right? And so in that case, like in the problem we did 1 or 0 as a base case, we can either do just even 0 as a base case, right? But the point is, once we get to num equals 0, then it looks like we stop, right? Because we don't say, what's the factorial of -1, -2, -3, and so forth. Like we stop at 0. And so basically, if we now go to our decision tree now, we basically say, hey, if it's any number that's greater than 0, let's just give me myself multiplied by the factorial of that number -1, right? If it's 0, on the other hand, I'm done. Okay, so let's look at how that looks in practice. In this case, what this factorial says is, hey, if num equals 0 or num equals 1, we return 1, right? Why do we return 1? Because we're just going to kind of say, hey, the factorial of 0 is 1, the factorial of 1 is 1. If you hit 0 or 1, here's a 1, right? Like that's the total. Like that's the total that you were expecting. And here we just test it out. So once we've established that the factorial of 0 is 1 and the factorial of 8 is 1, the factorial of any other number that's greater than, I guess, 0 or greater than 1 is equal to what? So this is undefined because we haven't defined it yet. Factorial of 2 then just becomes the number multiplied by the factorial of 1 less than it. And I'm going to skip through some of these slides really quick because they're a little bit onerous, right? Essentially, ignore the console log for now. This is saying, hey, if I give you a number, right? If that number is 0 or 1, I just want you to give me 1. That's the total I care about. Nothing else matters, right? Your total is going to be 1. On the other hand, if I give you any other number, the total is going to be yourself multiplied by the factorial of 1 less than you, right? So if I give you 6, it'll say, am I 0 or 1? No. Great. So then your total is going to be 6, u, multiplied by u minus 1, which is factorial of 5. Right? And so that becomes the entire kind of mini problem that we're solving here is when I give a function a number, all I need to do is figure out, do I stop or do I keep going? If I keep going, what number do I feed into the next iteration of this function? So, again, okay, cool. Okay. This is basically an extension of that, right? Notice how line 8 will never run if num is 0 or num is 1, right? In the previous countdown example, we put this in an else clause. Here, we don't have to put this in an else clause. The else is implied. And the reason why is because if num is 0 or num is 1, we're going to return 1, which means we're done with this entire factorial function. Line 8 and line 9 will never run. The only way we ever hit line 8 or line 9 is if we don't go into this for loop. Do you see that? So implicitly, there is this idea that like, hey, this line 6 through 9, this only applies if this if clause does not trigger. If the if clause triggers, we return 1. We're done with the factorial function. We don't keep going, right? Once again, as soon as we hit a return, the function ends right there. Nothing else coming after it matters. Okay, so if I hit line 8, it means it's implied that num is not 0 and it's not 1. Ever see that? Okay. So now my function does become a decision tree, right? The first thing I check is, do I stop? When do I stop? If num is 0 or num is 1, in which case I say, here's a 1, like, that's my answer. This entire function is over. If it's not 0 or 1, then I say, okay, great. I'm going to give you back my result. My result is going to be myself multiplied by the factorial of a number 1 less than me, right? What this is going to do now is this is going to trigger another function call called factorial, right? And if that factorial, no matter what it returns, I'm going to replace this with the number. I'm going to multiply that by myself, and I'm going to return that number. So let's see how it works. And I saw your question in the mirror. Give me 1 second. I'm just going to finish running through this example first. Okay. So if for factorial 5, let's see how this will actually look in like real term, right? The first thing run is factorial 5. Is 5 equal to 0 or 1? No, it's not. So then we skip lines 3 through 5, and now we're on line 7. Line 7 says, hey, calculate for me the num multiplied by the factorial of 1 less than factorial 4, right? And at this point, this function say, well, I don't know what factorial 4 is, or rather, I have to invoke factorial 4 so it can tell me what it is, right? So this means we need to add factorial 4 to our call stack. Factorial 4 is going to say, okay, I'm not 0 or 1, and my answer for you is going to be 4 multiplied by factorial of 3. I don't know what factorial 3 is, so let me calculate that for you really quick so I can figure it out. Factorial 3, 2, 1, and then finally, here's where we stop, right? Factorial 2 is equal to 2 multiplied by factorial 1. Factorial 1, we go here, we say, is num 0 or 1? And it's like, yeah, it's 1. Great. So the answer is 1, right? Like, line 7 through 8 doesn't matter anymore, right? We never hit line 7 through 8, because as soon as we say num is equal to 1, we return 1. And notice how now we've just returned 1, right? Factorial of 1 is 1. So once we're done with factorial 1, we give back 1. Now the question becomes, by the way, who asked for factorial 1? Oh, factorial 2 asked for factorial 1 because it says my answer is going to be 2 multiplied by factorial of 1. So now this just becomes 2 multiplied by 1, right? Factorial 2 says result is 2 multiplied by 1, so it's 2. I'm going to return that 2. By the way, who asked for factorial 2? Oh, right, factorial of 3 asked for factorial 2 because it says factorial of 3 is equal to 3 multiplied by factorial of 2. So if factorial 2 is 2, we then slot 2 into that factorial of 2, and now we say factorial of 3 is equal to 6. Who asked for factorial of 6? Sorry, factorial of 3. Factorial of 4 did. So great, let's slot that back in. Factorial of 4 is equal to now to 24. And who asked for factorial of 4? Factorial of 5 did, right? So now when we go back to our original factorial of 5, you'll notice that result is now 5 times 24, which is 120. And then factorial of 5 says, okay, great. The answer you were looking for is 120. Right? I can't stress enough that each of these is an individual function call. So the fact that factorial of 2 returns a number, it doesn't end factorial of 3. It only ends factorial of 2, right? A return statement in a function only ends that function. So factorial of 2 is going to say, I'm going to return a number, I'm done. But it's up to factorial of 3 to say, okay, great, I'm going to do 3 multiplied by factorial of 2. I get, I guess 6. Let me return 6, and now I'm done, right? So each of these functions are independent of one another in the sense that just because one thing returns, it doesn't kill the rest of the functions, right? If I had a series of for loops, it would be different because if one for loop returns something, it would kill the entire function, right? But because each of these are independent functions, they can each return something without killing the rest of the functions in its call stack. So we go to the very end, and now we have factorial of 5 is equal to 120. And that's it. So once again, our takeaways here, right? Write your base case first, always know when to stop, and generally speaking, when you're testing recursion, it's easier to test it with smaller inputs than larger inputs. Usually because your base case is going to be like a super small input, and then everything else should work, right? Like if it works for like anything like larger than your base case, it should work for all things larger than your base case. And then lastly is as you test it, like you do want to test it, but also just know that recursive functions are very like memory processing heavy, so you always want to be careful about how many kind of operations you have going at once. For this class, for this workshop, it won't be a concern, but just like more like in the real world. Yeah. Okay. So once again, recursion works. It's basically a function, right? Recursion itself is more of a principle or an idea. Right now, we're just using normal functions, so you can do all the things we've done normally with recursion. In terms of using any data type, we can go through arrays, strings, whatever it is that you want, as long as we set up correctly. And yeah, this last bullet is just a really long way of saying, once again, if you go through anything, the point is you want to get closer and closer to stopping, right? So if you're going through a string, you want to get closer and closer to the end of the string. If you're going through an array, you want to get closer and closer to the end of the array. If you're going through a number, you want to get closer and closer to whenever you want to stop doing that number. Yeah, I mean, these are just like super simple generic tips. You can read these yourself. There's nothing here I haven't said already. Okay, so any questions for kind of this morning session on recursion? Yeah.
I'm trying to wrap my head around recursion with strings. What would the base case be for a string normally?
It depends. What do you want? What's your problem trying to do?
I don't know. I'm just getting it with numbers, but thinking like, whoa.
Well, so let's say you're trying to figure out like how many vowels are in a string, right? You would go through it one character at a time, right? So if I was to write a function that counts a number, or rather that counts a number of vowels, right? One of the things I could be doing is I could say, okay, I'm only going to look at the first letter in the string, and then I'm going to recursively call myself with the string minus the first letter. And so my base case would be, if ever I get an empty string, it means I'm done, right? So with each iteration, I'm looking at one less character than the guy before me did, right? With an array, same idea. It's like you can basically give it smaller and smaller inputs, and your base case say, hey, when the input is null, or when we reach like the flat line for the input, we're done.
So like the base case would sometimes be like string length minus 1.
Yes, or just string length equals 0, or if string equals empty string. Probably the second one. Siori?
This is just a joke question about base cases. I mean, excuse me, call stacks. But what makes like call stacks, if I'm understanding them correctly, like recursion exclusive? Like how isn't the same concept used for for loops and every other kind of loop that we use?
Yeah, kind of. Yeah. Recursion just it's just super imperative for recursion because you're calling something kind of potentially infinite times. So you definitely need to have it. Although you're absolutely right, like the conditional for the base case, or sorry, the conditional clause for the for loops does something very similar.
Okay, just to make sure.
Yep.
We were only bringing it up.
And then Amir, do you have a question too?
It was just like a minor thing I wanted to clarify.
Sure.
You did or num equals 1, right?
This is the factorial problem?
Right. Yeah.
Yep.
That isn't really necessary, right? That's just to save one extra step.
Sorry, which line?
Or num equals 1.
Or num equals.
Like if num equals 0 or num equals 1, like this problem could work if it was just if num equals 0, return 1.
Yeah, it could also work there too. Yep.
But what about num is less than 1?
Won't we ever? Well, so that's something you would need to figure out, like probably even before that. Like the idea is like, I don't know how. Like I think the mathematical way to calculate factorial for a negative number is different, if you even can. So like this function would just like not work at all, right? Like this function is written so that it handles like the cases for which it's able to handle. If you want to say, if you wanted to add a check even before on line 2, it says, if num is less than 0, then you probably want to do something else entirely different. Any other questions? All good? All right. I'll let you get started on your workshops.